All right, so the second half of chapter 6 here is continuing on with these probability distributions, but we're going to talk about what's called a binomial probability distribution. So we will decide, do we have a binomial experiment? We will compute probabilities from that binomial experiment, find the mean and standard deviation from a binomial experiment here, as well as graph a binomial probability distribution. What is a binomial experiment? So we just finished talking about what's a probability distribution. We're now going to talk about a binomial probability distribution. So this is a discrete probability distribution, but it's going to describe probabilities for experiments in which there are only two outcomes, and those two outcomes cannot overlap. They're called mutually exclusive, also known as disjoint. This only has two choices: a success. So if we go back to the making a free throw, yes, you make it, or a failure, no, you don't. The only two things we're talking about are, were you successful, were you not, and what's the probability that you get so many successes and so many failures. Any experiment where we only have these two outcomes are called binomial experiments. So bi meaning two outcomes, success and failure. But again, just like every other distribution we work with, there are certain things that have to happen. An experiment will be binomial if, number one, the experiment is performed a fixed number of times, and each repetition of the experiment is called a trial. So from the beginning, you'll say, I am going to repeat this experiment 10 times, and then I'm going to, each time I do it is a trial. Each trial is independent. That means that one trial does not impact the outcomes for the next trial. For each trial, again, there are only two outcomes, either success or failure. The probability of success is going to be fixed for every single trial of the experiment. Anytime we talk about a random variable, it would be capital X. And then this time we are going to talk about a binomial random variable. Okay, so anytime we talk about these random variables, they're X's, but they can be discrete, they can be binomial, they can be normal, uniform. We'll talk about them all. All right, what happens in a binomial probability distribution? We will have n independent trials of an experiment. We will have a P, which denotes the probability of success for the trial. So if we subtract that value from 1, that is the probability that we fail. For example, 60% successes, 40% failures. And then X is going to denote the number of successes. So we'll figure out, what's the probability of getting 6 successes out of 10? All right. So the number of successes we want has to be a whole number, and each one is independent of the next. We're going to decide first, are these binomial experiments? So for those that are binomial, we will identify the number of trials, the probability of success, the probability of a failure, and possible values that we could ask. Okay, number 1. An experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. They're only asking for 2 things here: makes or doesn't. So makes 80%, misses 20% of the time. He is asked to shoot 3 of them. 3 independent trials. He could make possibilities, none of them, 1 of them, 2 of them, or all 3. And this makes it a binomial experiment. So let me erase my writing here so you can see. actual text here. I like to work it out with you first, though. There are 3 trials. The trials are independent. There are 2 possible outcomes, make or miss. The probability of making it is 0.8. The probability of missing is 0.2. And the possibilities are 0, 1, 2, and 3. So all of the things we said, yes, this is a binomial experiment. According to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained and the number of Americans who choose chocolate as their favorite ice cream flavor is recorded. Going to be again. Here's why. 10 trials. Each person I talk to is going to give me their favorite flavor. And each person is independent from the next. You are looking for 2 possibilities. Either they like chocolate or they do not. Probability of getting a success is 28% or 0.28. So the probability of getting a failure is 1 minus that, or 0.72, 72%. And in our random sample of 10, we could have none, 1, 2, 3, all the way up to 10 that choose chocolate. We could have any one of those possibilities be our 10. And if we sampled another 10, it could be a different value. Who said chocolate was their favorite? A probability experiment in which 3 cards are drawn from a deck without replacing, and the number of aces is recorded. Problem right here, without replacement, immediately tells me that that is a dependent probability. So this does not work. If I do not replace the cards, the next card I draw is dependent on what I already drew. So this will not work. If we did a with replacement, then it may work. But this one's not going to work because the second time through, our probability is different. Note that the word success does not always have to imply something positive. Success means that an outcome has occurred that corresponds with P, the probability of success. How do we actually compute these probabilities? Well, there is a lovely formula using our combination equation from chapter 5, also with multiplying probabilities to a power and then failures to a power. It's a messy, messy equation. We're not going to use the equation, just like we haven't used the equation before. We use stack friends to help us. So I will show you how to do that. One thing that we are going to come across here, though, is they're going to have different phrases in these questions, and different phrases mean different mathematical symbols. So you may want to like cut out or star this table or do something so that you have this table accessible to you, so that when you go and look at these problems, like you have this available so that you know which symbol it means. At least, also known as no less than or greater than or equal to. More than or greater than is greater than. Fewer than or less than symbol. No more than, at most, or less than or equal to is a less than or equal to symbol. Exactly, equals, or is the equals equation. According to CTIA, 72% of all adult Americans would rather give up chocolate than their cell phone. In a random sample of 10 adults, what is the probability that exactly 8 would give up chocolate? My step crunch back here. All right, so where we're going to go for these is we're going to go to stats, calculators, and then binomial. We have to enter a few things here. The first is N, how many people we have asked here, and that is 10. P is the probability of a success that they give us. So 72%, which is 0.72. And then we have options here. So if we're asking for a single value here, less than or equal to, less than, greater than or equal to, less than, greater than or equal to, we can use that here. Or we have the option here to do between two values. So this one says exactly 8. So N is 10, P is 0.72. Again, we went to stat, calculator, binomial, and we want exactly 8. So we want the probability that X is equal to 8, only 8. So let me get back up here. So I'm going to go back to standard here. I want equals to 8. Click enter, and you'll see here that the red one is highlighted in red. Sorry, the 8 is highlighted in red because that is the one we're using. That is the one we're looking for. So it will always highlight the values that you are accounting for in your probability distribution. Okay, so our answer is going to be spit out over here. So 0.255 roughly, 0.255. On the next slide here is the interpretation of that value. The probability of getting exactly 8 adult Americans out of 10 who would rather give up chocolate is 0.2548. So if I were to repeat this 100 times, grab 10 people here, grab 10 people there, grab 10 people there. Out of those 100 trials, about 25 of them, I would expect to have 8 Americans say that, yeah, give up chocolate instead of their phone. What if we want to find fewer than 3? Well, that's a probability. So fewer than is the same as less than 3. So probability of our value is less than 3. So that's going to include the ones that say 0, 1, and 2. It's not going to include 3 because I want smaller than 3. So when I go back here, same graph that I was on, but I want to do less than 3. So you'll see here, when I hit enter, it's going to highlight 0, 1, and 2. And of course, I don't have 0 on my graph here. It only shows 2 to 10. I was hoping there was a way to see the values smaller than that, but it's not showing it to me. Probability of getting less than 3, super duper 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 small, 0.00096. 1, 2, 3 zeros. Phrase fewer than means less than. Already did that. So our interpretation here is 0.00096. So if I were to do that, I can't even do it in 100 trials because it doesn't even, this is decimal is so small. It's basically about 1 in 1,000. So it's really not likely to only find less than 3. Okay, find nobody or 1 or 2. It's not likely that this is going to happen. C, at least 3. Well, at least 3, if you have to go back to the table, you can, but at least 3 means greater than or equal to 3. Let's back up. Change this to greater than or equal to. And that is, of course, the complement. All the values I didn't use. So 0.999. It is the complement of this one. The probability that in a random sample of 10 adults, at least 3 would give up chocolate than their cell phone is 0.999. So basically 999 out of 1,000. We would get some 3, 4, 5, 6, 7, 8, 9, or 10 adults saying that they would rather give up chocolate than their cell phone. I don't really want to give up either. I like both. This one here is a between. So how about we get between 5 and 7 inclusive? So that means I'm including 5 and 7. So 5 less than or equal to x less than or equal to 7 is what it's going to look like when I go to my between here. So 5 and 7. So you'll see here we've included 5, 6, and 7, added them together here. 0.5 to, I'm going to round to 8, 0.5 to 8. Basically what I've already said there. So 5, 6, and 7, add them all together, 5, 2, 7, 9, or my 5 to 8. So about 53 out of 100 or 528 out of 1,000. If I did this, we'd come up with 5, somewhere between 5 and 7. They said they'd rather give up chocolate. According to the Gallup organization, 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, what's the probability that we get exactly 10 and then no more than 6? Here's our probability. Here's our N. So N is 15. And it was 68, right? Nope, 65. Okay, so first one is exactly 10. So that's equal to 10. Enter your N, enter your P, and then select what you want. We want exactly 10. So exactly 10 is 0.212. Equals 10.212. And let the homework will dictate how many places you go to. 3, 4, 2 decimal places, whatever it asks for. This one, no more than 6. That means I can include 6, but I want less than, smaller than those values. So P, no more than, is less than or equal to 6. And pull back up my graph. And then change this to less than or equal to, change that to 6. And you'll see the red ones are highlighted, 6 and below, 0.042. Okay, and then I have the graphs copied over here. You can see here, exactly 10 was 0.212. So if I did out of 100, 21 out of 100. If I did it out of 1,000, 212 out of 1,000, I would get 10 out of my 15 to say they favored the death penalty. Oops, apparently I didn't put these answers up here. I apologize, but I did show you these answers. All right, so how do we calculate a mean and standard deviation when we have this random variable thing going on? Well, the mean, also called the expected value, and standard deviation are two basic formulas here. These are going to carry across with us as we go into 7, 8 on. A binomial experiment with n independent trials and probability of success p is going to have a mean that takes your number of trials times your p, and your standard deviation is the square root of n times the probability of success times the probability of failures. Okay, so if we go back to that heating up of chocolate rather than your cell phone, we have, again, our P is 0.72 and our N this time is 300. Determine the mean and standard deviation for this situation. All right, well, the mean is just N times P. I'll take 300 times 0.72, and you just grab a calculator. And you'll get 216. The standard deviation is the square root of n times p times 1 minus p. So the square root of 300 times 0.72 times 1 minus 0.72. If you want to double check that you're entering those in a calculator correctly, I'll give you just a second here. Get my decimals open. And find my square root. The square root of 300 times 0.72 times open parentheses 1 minus 0.72. Here we go. So 7.777. I do have the calculations underneath there as well. Values we just got. Again, let homework tell you how far to run to. Is round 2. So basically, what this means is if we were to take 300 people, we would expect about 216 of them to give up chocolate over their cell phone. How do we graph them? Well, hey, guess what? I've already kind of been showing you the graph in how we were doing our calculations here. So you kind of already know this part here. We'll just talk about it real fast here. So we can graph the probability. The biggest thing that we're going to talk about here, though, is what happens to the shape then. So different graphs can have different shapes. Remember, we have uniform, we have normal graphs, we have skewed to the left and skewed to the right. So these binomial graphs can also have those shapes. We've been doing this. In case you don't remember where I got there, it was staff, calculators, and binomial. This one was 10 and 0.2. And you can just hit enter. You don't have to worry about the filling in the probability part here. You can just do it right here. So it's going to automatically highlight, like I said, some of those colors. But I have the graph here on, oh geez, that's got all the values on it. So here's the graph. Same graph that we got. You can pull it up here if you don't believe me. So what it looks like StatCrunch does, though, is these values that are almost negligible, almost zeros, they don't graph them. So you'll see here 0 has a value, 1, 2, 3, 4, 5, 6 has a value, but 7, 8, 9, and 10 are really like non-existent here. Their probabilities are so small, so the graph isn't showing it to you. But we do have a total of 10 values, so we do have to know all the way to 10. If I look at the whole graph all the way to 10, we find our peak. And you will see here that the right tail is longer, so we are right skewed. So working with the theme, 10, but changing the probability to 0.5. Okay, it's going to make it exactly symmetric. Why? Well, let's go back here. The probability is 20. So 20% should be the highest. 20 out of 10, 2 out of 10 is that 20%. That's the highest peak. So the middle here, if I do 5, there's the middle. And then look, it's now symmetric on both sides. So this one is going to be symmetric. And guess what? If I move that probability to the right, we're now going to be skewed the other direction. That peak is going to be at 8. 8 out of 10 is 80%. And then we're skewed back this way. So this here is giving you all the values. They're calculating every single one. You don't have to do that, okay? So we're just going to work with the graphs. 8 is the peak. There are more values to the left than the right, so we are left skewed. We can see how P plays a role in the shape of our binomial distribution. So we kind of talked about it here. P, back here, when we looked at the different P's, it can change it. So what does N do? Here's what they did. They kept P 0.2, N and 10. So here's this one. And our peak was at 2. Okay. It kept the probability 0.2, but then bumped it up to 30. And it looks like the middle's now here. But it's still kind of skewed to this right-hand side. Okay, this last one, I increased my total up to 70. And now it looks like, there's kind of my middle, it looks a lot more normal. Okay, so P can skew our graph left and right. What does N do? Well, the larger we sample, the more normal our curve is going to look, or our distribution is going to look. If we keep P fixed, as we increase the number of trials in our binomial experiment, the random variable is going to become more bell-shaped. As a rule of thumb, if I calculate NP times 1 minus P and I get greater than or equal to 10, the probability distribution will be approximately bell-shaped. This is something we will discuss in chapter 7, because for now, this is the only way we know how to solve these. Okay, 7 talks about what the normal curve is and how we work with the normal curve and probabilities from the normal curve. And if we have enough information, we could actually use the normal curve instead of this binomial. So we are going to lead into that in chapter 7. Let me grab back up the homework. So let's see if there's any other ones we want to look at. Okay, so some definitions. Is it a binomial experiment? Is it a binomial experiment? Yes or no? So then we're going to calculate some probabilities given NP and equal to 7. We've got NP, we want a less than or equal to 3. I think those are pretty straightforward. Some of these you'll have to, let's see, read them carefully. Okay, find the mean and standard deviation. All right, so this is like the longest one. Let's try this one. So yours will be similar to mine. All right, in a remote sample of 15 women 18 years or older, find the probability that exactly 10 believe the minimum driving age should be 18. Right, we've got a 60% value and we are sampling 15. We've got 15 and our probability is 0.60. Exactly 10. So we'll do an equals to 0.18. So there's 4 decimal places. So 5, right? Okay. Next one, fewer than 5. So fewer than means less than 5. So 0.000934 does not round the 3 up. So there we go. Okay, next one says at least 5. At least is the symbol greater than or equal to. So 99065 is going to round that up to 7. Okay. Next one wants between 7 and 12. Sorry, I keep right clicking. So between 7 and 12. So really straightforward in using the calculator here. Just have to make sure you read those symbols, read the terms carefully to know which symbol you need to use. Okay. In a random sample of 200 women, 18 years or older from the nation, what is the expected number who believe the minimum driving age should be 18? And what is the standard deviation? Okay, so now we have to find the mean and standard deviation. So remember that expected value is mean and standard deviation we'll calculate here. So mean is your total 200 times your p, 0.60. So mean is 120. And then standard deviation, where's my square root symbol? Gotta get the square root symbol there. Quick. Okay, so square roots of 200 times 0.60 times 1 minus 0.60. All right, standard deviation says to go to one place, so 6.9. If a random sample of 200 women 18 years or older from the nation resulted in 110 who believe that the minimum driving age should be 18, would this be unusual, and why? So let's go back. Calculators, binomial. We're gonna do 200 is 0.6. And we want less than 110. Okay. So 110, that is not unusual value. Usually unusual, in order for it to be unusual, it's gonna be 0.05 on one side, and that would then make it more than 2 standard deviations away. One other way to do this is I could check the z-score. So to find the z-score, you take the data value in question, 110, minus the mean, 120, and take that divided by the standard deviation. So take negative 10 divided by our standard deviation, 6.9. Okay, this is less than 2 standard deviations away. This is not 2 standard deviations away, so this is not unusual. Okay, if I asked for, let's say 100, let's try that one. 100 minus 120, that's negative 20. If I take, golly days, negative 20 divided by 6.9, that is more than 2 standard deviations away. That's almost 3 standard deviations away, and then that would be considered unusual. Okay, so this is going to kind of lead us into where we're going in chapter 7. So it's just on there once, but I thought I would show it to you first. But yeah, that's the end of chapter 6. I hope it wasn't too bad for you. StatCrunch does a really great job of just being that tool to help you visualize it and come up with the answers as well. So if you have any questions in the meantime, don't hesitate to shoot me an email. Otherwise, I'll see you back for chapter 7.